Okay, so before we get started with this problem, I want to identify that our constraint is given right here. So this is our constraint. And this is given to us in the form g of xy equals k. So on the right-hand side, we have k equals 1, and on the left-hand side, we have our function g of xy, which is x squared plus y squared. Okay, so let's get started. We've got two equations we need to work with. We need to find... Okay, so let's get started. So we've got f of xy is x squared plus 2y squared, and we'll need to find the gradient of f. The gradient of f is the vector 2x comma 4y. We'll also need g of xy, which is x squared plus y squared, and the gradient of g of xy is just 2x 2y. So now let's set up our equations. We've got the gradient of f equals lambda times the gradient of g. We also need to work with this constraint that g of xy equals k. Okay, so on the left-hand side, we've got the gradient of f, which is the vector 2x 4y, and that's supposed to equal lambda times the gradient of g being 2x comma 2y. We will need to solve that equation for x and y. Over here we've got our constraint. We must satisfy that x squared plus y squared equals 1. Okay, so let's work this out. If these two vectors have any hope of being equal, it must be the case that 2x equals lambda times 2x. And equating second components, it must be true that 4y equals lambda times 2y. Okay, so let's subtract. So we have on the left-hand side 2x minus lambda 2x equals 0. And we have 4y minus lambda 2y equals 0. Pulling out common factors, on the left-hand side we'll have a 2x parentheses 1 minus lambda equals 0. And so what this tells us is that either x equals 0 or lambda equals 1. For the second equation, we pull out a 2y and we're left with 2 minus lambda equals 0. And this tells us that either y equals 0 or lambda equals. We now need to work with our constraint to make sure whatever values of x and y and lambda we're picking, that they satisfy the constraint. Okay, so let's make a note of that. We need to satisfy. Okay, so let's think this through a little bit. We'll have a few cases here. So the first case I want to think about, if x equals 0, what does that tell us? Well, we must satisfy the constraint which says that x squared plus y squared equals 1. And so if x equals 0, it must be the case that y squared equals 1. In other words, y equals plus or minus 1. Okay, so we get x0, y1, or x0, y negative 1. Let's look at another case. What happens if lambda equals 1? So what happens if lambda equals 1? Well, if lambda equals 1, down here on the second line, let's see, lambda is not going to be 2 because we said lambda is equal to 1, so it must be the case that y equals 0. If lambda equals 1, then lambda cannot be equal to 2, and so y must be equal to 0. If y equals 0, we have to satisfy the constraint, x squared plus y squared equals 1. What do we get here? We get x squared equals 1, x equals plus or minus 1, and we're looking at 1 comma 0 and negative 1 comma 0 as being the resulting xy points that we get here. Okay, so we've treated those two cases. Let's look at what happens on the second line. On the second line, if y equals 0, well, we already know what's happened because we analyzed case 2, and that was y equals 0. So there's no more analysis we need to do. Similarly, if lambda equals 2, then we go up here, lambda cannot be equal to 1, and we're simply looking at the x equals 0 case, and we've already covered that in case 1. So the only points that we get out of this analysis are the following 4 points. So the extreme values of f, subject to our constraint, which is x squared plus y squared equals 1, these extreme values lie at either 0, 1, 0, negative 1, 1, 0, or negative 1, 0. So we need to figure out which of those is going to produce a max and which of those is going to produce a min. Okay, so now let's test the values. We have x, y points that we're going to test, and we're going to plug them into f and see if they yield maximums or minimums. So the points that we need to test are 0, 1, 0, negative 1, 1, 0, and a negative 1, 0. Plugging those in, remember f of x, y, this looked like x squared plus 2y squared, so let's plug in f of 0, 1, we get 2. F of 0, negative 1, we get 2. F of 1, 0, we get 1. And f of negative 1, 0 gives us 1. So what does this tell us? This tells us that the max value of f is 2. And this occurs at 2 places. It occurs at 0, 1, and 0, negative 1. We also found a min value of f, subject to the constraint, and this occurs at 1, 0, and negative 1, 0. So what is the picture of this? What's really going on here? Let's take a look at a visualization of this particular function. So we're going to graph our surface, x, y, z. So we're going to graph our surface here. I'm going to graph f of x, y equals x squared plus 2y squared, and that is some sort of surface like this. Looks like an elliptic paraboloid. Okay, so it's got some shading there. And the constraint is the circle x squared plus y squared equals 1, and that circle lives down here in the xy plane. And the idea with this analysis, if you pick a point like 0, 1, okay, that lives on the constraint. And you take that point and you f it, you apply f of 0, 1, you get up here to some point in 3 space. It's over 0, 1, up 2, right? We did that analysis right here. And if you went and you did that for all the little points that live down in that circle, you'd get a kind of a curve, or it looks almost like a belt lying on this surface, right? It just wiggles around on the surface. You get a curve on the surface and it goes around the back side there. And that is f subject to the constraint. And we found that the max value of f subject to the constraint lies here at 2, and the min value, if you take that point and you apply the function to it, you get 1, 0, 1. The min value lies right there.